Hi, and welcome to this video about Greybox parameter estimation. In this video I will go through the mathematical foundation of this framework which we call Greybox models. And as we will see, this topic has also implications for parameter estimation of dynamic system models in general, and I will explain in detail all of these concepts as we go through the slides. The agenda for this presentation is going to first be some general notions of what stochastic dynamic models are, why we call it Greybox, and what the topic of state filtering has to do with Greybox models. I will then go through this concept of parameter estimation and what it has to do with the likelihood function, and also what Kalman filtering does in this sense, in this framework. We will say something about numerical optimization, gradient descent methods and so on, as well as other methods that can be used for parameter estimation in this Greybox setting. We will also discuss how can we quantify uncertainty. As we know, nothing in this world is certain, and that applies especially to estimated parameters, and therefore it's important to have some tools to express the uncertainty of our estimation. Finally, we will discuss model selection and validation, as well as the parameter identifiability. This is also a very important topic when we deal with parameter estimation, to know in what cases the parameters that we are looking for can or cannot be identified. So all of these topics is related to parameter estimation for dynamic system models, especially models which are estimated under some uncertainty, that is either uncertain models or uncertain measurements, or as is almost always the case, both. And I will explain all of this in some detail. Of course, this is a lot of topics, so there is no way I can give an in-depth discussion on all of these things in one video. So this is more of an overview to help to get the complete broad picture of Greybox models and parameter estimation in general, and to encourage you to continue studying these topics on your own with the help of all the relevant literature that is out there on all of these different topics. Before I start, I want to say that this topic is somewhat theoretically complex, and the video therefore requires some prerequisite knowledge in typical cybernetic engineering things like Kalman filtering, state estimation. It's useful to have some insight into what parameter estimation is all about, as well as some basic knowledge on statistics and mathematics. So it's useful to keep that in mind, because I will not explain all of these things in very low, from the ground up, so to say. It will be, I will assume some prerequisite knowledge as we go through all of these topics. So to start out with, we need to talk about this idea of stochastic dynamic models, or Greybox models as they are typically referred to. So why do we call it Greybox models? Well, when we want to make a model of a dynamic system, there are basically two diametrically opposite ways that we can approach this task. The one approach is what we call a white box model, which is we use our own understanding, our human expert knowledge about how a certain system or a process operates, and we describe the physics of that process using equations. So that's a model which is interpretable, which is basically just our own mathematical description of how we understand a certain process to operate. And therefore we call it white box, meaning that it's readable, interpretable. And this type of models, they tend to generalize well between different systems, because they are a description of a general understanding of a system. Another alternative is what we call black box models, or data-driven modeling. And this is an approach where we don't use any of our own understanding of the system, but instead we have some general structure, like an Armax model or a subspace identification matrix, and we use a set of data to calibrate the parameters of this model. And the data then represents empirical knowledge. That's some measured historic information about how the process operates. So that's in contrast to what we had over here, which is the expert human knowledge, which is encoded in mathematics. Whereas over here we have the empirical knowledge, which is encoded in the data. And then we use some sort of mathematical magic to calibrate the parameters of a model structure. The downside of the black box framework is that those general mathematical structures, say for example a neural network, they tend to be very difficult to interpret. They don't provide a description of the underlying system which is easy for a human to understand. But they can be used to simulate its behavior, so it's possible to sort of use them to understand the underlying system's behavior anyway, but only sort of through simulation or through mathematics. It's not really understandable or readable in the same sense as a white box model, and that's where the term black comes from. The advantage is that models that are calibrated to data from a specific system tends to have better prediction accuracy, because they are based on information that is specific for one instance of a process, not a sort of general description of the physics of a process which we use in white box models. And in this sense, we can think about Greybox models as almost a sort of a literal in-between of those two extremes, where we want to combine the best of both worlds. So we want some sort of physical knowledge which gives us a model structure, and we want to use data to calibrate some or all of the parameters of that model structure. So we do use our expert knowledge to design a model structure, and then we use data to calibrate the parameters. And this is a very interesting approach, as we will see throughout this presentation, because if done right, this has some very nice properties. And we can even think of it as sort of a generalization of both of these white and black approaches, because Greybox in the extreme could be just a physical structure, then it becomes white, or it could be a completely general structure with all the parameters free to be estimated, in which case it becomes sort of almost black. So this has been argued as sort of a natural framework for dynamic system models in general, because it's more general than this black box or the white box approach by themselves. So some thoughts on the idea of the Greybox modeling framework, just to sort of clarify what we will understand by this term for the purpose of this presentation. So the estimation of unknown parameters in a known model structure, which is at least partially derived from physics. So that means we use some physical knowledge to construct the model structure. It's not just completely general model structures, it's some representation of our own physical understanding of the underlying system, but still with some parameters that have to be estimated, either because they are unknown or they could be so-called lumped parameters, parameters which represent sort of a combined physical effect. And this indeed turns out to be a very good approach for parameter identification or parameter estimation for dynamic systems models in general. As we will come back to later, it could be argued that since all models are in some sense wrong, all models are actually in some sense gray. It's more of a philosophical discussion, but very few models are truly white box. There is always some uncertainty involved in the formulation of a physics-based model. And equivalently, very few models are truly black box, because we always use some sort of physical understanding of the underlying system in designing or choosing this general mathematical structure. So it could be philosophically at least argued that all models are in some sense gray, and therefore an in-depth study of this idea or notion of a Greybox modeling framework is really worthwhile, because it helps us to generalize parameter estimation to other types of model structures, which is sort of closer to the pure white or to the pure black box paradigms. And just as a sort of a note, for the purpose of this talk, we will focus on what we will call offline methods, which is methods for parameter estimation, where we assume that we have some sequence of data that has been collected, and that the parameters are reasonably constant, meaning that we will find one constant parameter value for our data set, so the parameters don't change throughout the data set. Of course, the process could then be repeated for a new consecutive data set in which you might find a slightly modified version of or value for our parameters. So it's not to say that the parameters have to be completely constant for all eternity, but they are at least treated as constants for the chunk of data that we use to calibrate them. This is in contrast to this idea of dual estimation in a Kalman filter, where you augment the state vector with parameters. That's not what we are dealing with here. We treat the parameters as constants. It's useful to start with some sort of formal notion of what we mean with stochastic dynamic system or stochastic dynamic model. And this is sort of just a mathematical generalization of the idea that we have a Greybox model, that is something which is known and something which is unknown. And that's where this sort of idea of stochasticity comes in, that something is unknown. And we will formulate that as this equation here shows, where we have a stochastic differential equation for the state transition term, and then we have an algebraic equation for the measurement term. And just to get the formalities out of the way, we need to define a set of parameters, which we will call theta. And then we have a continuous time state transition equation, which we consist of two terms. We have the state transition itself, which is f, which is commonly called the drift term. And then we have this expression here, which is some formulation of the uncertainty of the state transition. So that is called the diffusion term. So this says that the time derivative of the state vector has one term which is known and one term which is stochastic, which means it's not known, but it's still possible to say something about how this behaves. And then we have a discrete time measurement equation. That is, we have a measurement model, which is our h function up here. So that's a mapping which tells us what the output of the measurements of our model is, given the known states. But there is also some uncertainty in the measurements, so we have to add this component of measurements noise vk up here. So this shows that we have uncertainty both on the measurements, which is sort of the, I guess, most easy to come to grips with, that measurements are uncertain, there's always noise in measurements. But we also have some uncertainty up here, meaning that we have an imperfect model. That is, our model is not capable of exactly describing how our underlying system works, which is kind of where also a different perspective on this term gray, that the model is imperfect. It's not an exact description of the underlying system. Yeah, it's useful here to just, I guess, note as an anecdotal comment that when we talk about uncertainty here, it's useful to distinguish sometimes between different kinds of uncertainty. So I will use sometimes the term aleatoric uncertainty, which means something that is truly random, like thermal noise from an electronic circuit is typically considered to be truly random. It's driven by some quantum effects, so it's not predictable no matter how much information you have. This is sort of truly random effects. But there's also other kind of uncertainty which we call epistemic, and that is any uncertainty which comes from the lack of knowledge. So typically things like modeling errors. If our model has epistemic uncertainty, it's because we are missing some information that if we added it would remove the uncertainty. So typically for a simplified model, this is a very natural concept, that we choose to make a suboptimal model description of some process because we want as simple as possible a model. And then we sort of introduce this epistemic uncertainty because we neglect some details of the physical process. Of course, this is a very common thing to do in almost all modeling approaches, that we have to make some simplifications or assumptions. And this kind of simplifications and assumptions, they will introduce this epistemic type of uncertainty into our state transition. So some further comments on this diffusion term, which is very often in the cybernetics literature at least referred to as process uncertainty or model error. So we will see that we need a model for this diffusion term. And we can already now just sort of rest assured that we can turn to our commonly used normal distribution for that. It's always very nice if something can be modeled as normally distributed, because that normal distribution, as you probably know, has a lot of nice mathematical properties. It's easy to work with. So we will see later that it's possible to model this diffusion term as a normal distribution, and I will get back to why that's useful later. I just want to right now point out, since we are talking about uncertainty, that the reason we can do this, which is sometimes overlooked in lectures on cybernetics, is that we have a lot of different sources to this process uncertainty. It's not just one effect that gives us the process uncertainty. Process noise or process uncertainty is actually the combinations of multiple different effects, like model approximations, unmodeled disturbances. When we use data to calibrate it, we have, of course, noise on the measured inputs which we inject into the state transition. But the noise on inputs is usually not modeled in this standard state space descriptions. And therefore this also contributes to uncertainty in the state transition model. And the combinations of all of these effects, that's what gives us the process noise term, or the diffusion term. And it's known from statistical theory that if you have an addition of multiple random variables with different sort of distributions, they tend, in the limit of a very large number of random variables, which in reality doesn't have to really be that large, they tend in sum to behave as if though they are normal distributed. As an example, in embedded systems where we have usually limited access to libraries for different computer functions, if you want to make something make a random number or draw a random number from a normal distribution, one way to do that is to draw 20 numbers or something like 20 numbers from a uniform distribution and add them together. And then you will get something which behaves more or less like a normal distribution. That's basically the same effect, saying that if we have a large number of sources of uncertainty with different sort of distributions, they tend to behave as if normal distributed in sum, which is why we typically say that this is a reasonable approximation, that we treat this diffusion term as normal distributed. And indeed that is also why we, in the previous slide, used this symbol here, which is a Wiener process, which is a random walk normal distribution type thing to depict the diffusion term. So now we will move on to the idea of parameter estimation, and particularly we will discuss parameter estimation under model and measurement uncertainty. I will explain in detail why it's important to keep that in mind, that we look at the model as uncertain and the measurements as uncertain. But first, this idea of parameter estimation in dynamic models. So we said that we have some unknown parameters theta, and we also said that we have some known model structure, which we will call M. And the whole sort of point of parameter estimation, as you probably are aware, is that we want to compare the simulations or the predictions of our model to some set of measurements. And then we want to adjust these theta parameters until our model fits the measurements in some specific mathematical sense, typically something like a root mean square error or sum of square errors or minimum integrated absolute error or whatever you want. Heuristically, there is many approaches to this, but the fundamental idea is that we compare model prediction to measurement, and we try to tune the parameters until the model fits the measurements in some specific sense. Formally, we can write it as such that we have a parameter theta, which is the argument of an optimization function. Minimization, maximization depends a bit on how we define this g function. And then we have our parameters as an argument to this function, which we then wish to optimize. And typically this is subject to some constraints, that these parameters exist in some predefined parameter space. So it's not the whole space of all real numbers, but it's some constrained space, which we will call parameter space. And in this formal definition, we use the term g to describe the objective function. That is some sort of mathematical description of what it means for a model to be a good fit to the data. Like I said, it could be sum of square errors, it could be integrated absolute error, or indeed a whole bunch of other mathematical descriptions, but it has to have some sort of specific meaning. It's actually very important how we choose this g. We use the term m to define model structure. We also have a term here, k, which we use to stand for the contextual information. That is the measurements or the data set that we have to feed into this mapping in order to calculate what it means for a parameter to be a good fit. And also we, in the formal definition at least, explicitly state A, which stands for the optimization algorithm. Because it turns out that actually the choice of algorithm here can also have an influence on the resulting parameters of what we get out of this. So formally we include this A, but for the in the sequel, in the subsequent slides, we will simplify this to basically just say that g is a function of theta, and we will leave m, k, and a dependencies as implicitly stated from here on out. When talking about parameter estimation, the main sort of demarcation between different types of parameter estimation is actually how do we define this g function? How do we define the objective function? In dynamic systems, we can choose between stochastic or deterministic state transition equations, as we will get back to, and that directly influences how our g function looks like. And if we sort of go more into the heuristic domain of objective functions, there is a lot of different formulations that we can use that have different meaning. And that again gives us the different approaches to parameter estimation. And the second demarcation is of course also what type of algorithm is used to optimize this g function. So that's, we will see also there is many different choices for algorithms, not just numerical optimization, but we will also discuss Markov Chain Monte Carlo, for example. And there is also many others which we will not discuss, because then we will be here for a month. To start with, I want to show some examples of how we can approach fitting a model to measurements under uncertainty. So the first approach people learn, and people also use, I guess probably 99% of the time, is something which we call to fit sort of a simulated trajectory or a ballistic simulation. In this approach, we set some initial conditions for our model, and then we simply simulate the model throughout some data set. The whole sort of trajectory is simulated, and then after the simulation is complete, we compare the simulated values with the data. And we calculate these discrepancies here, which we call errors, and then we calculate, for example, the sum of square errors. And this is something sometimes known as a ballistic simulation, because we use only information at the starting point here, and everything else is up to the model. So this is like throwing a baseball, where after the ball leaves your hand, it leaves the initial state, there is really nothing we can do. It just follows its own trajectory, and it lands wherever the model says it lands. And then we compute the trajectory errors after we have completed the simulation. And we will see, and hopefully it will become obvious once we have really dug into this idea of stochastic parameter estimation, that this approach really implies that we trust the model completely, and that we treat all of the uncertainty as being on the measurements, that all of the uncertainty in the estimation problem is due to measurement noise or measurement uncertainty. Another approach is something called fitting the one step ahead predictions. So a completely different option here would be to say that we know the states of the model at some time. For example, if the states are completely measurable, we could start with known states, and then we could make a prediction, and then we could calculate the error between the predicted state and the actually measured state. And then we could repeat the process that we just from this new measured state calculate another prediction. And this approach actually implies that we completely trust the measurements, whereas we treat all of the uncertainty as being due to the model itself. And it's interesting to observe that when we deal with white box parameters, estimating parameters in a white box sense, which is sort of typical for physicists, they very often use something like this, where you just do the ballistic simulation and you trust your model, basically. So even though people are not aware of that, that's what they're actually doing. It's sort of intuitive that if you deal with white box models, that is models which is derived from your own expert opinion on how a system works, then you might be inclined to use this approach. Whereas if you deal with something like an Armax model, where clearly the model is uncertain because it's a completely general mathematical description, then you might typically use this approach. And that's very typical of this sort of black box paradigm. But we are not so interested in the scenarios where it's reasonable to completely trust the model or completely trust the data and assume model is uncertain. What we want to do is treat both model and the measurements as uncertain. More or less uncertain, that's a different discussion which we'll get back to. But at least there is some uncertainty related to the model and there is some uncertainty related to the measurements. So what can we do then? Well, it turns out that what we can do is something called state filtering. So we can, similarly to the one-step predictions, we can perform a prediction one step ahead. But rather than completely accepting the new measurement as determining what the state should be, we do a prediction correction scheme. So we use the model to predict one step ahead, and then we take into account the measurement in order to perform a correction on our predicted state. And then from this corrected state, we then again make another prediction and another correction by measurement again. And then we go through the whole data set in this way. And the actual balance then between how much we trust the model and how much we trust the measurement is quite literally given by this correction step. How much of the measurement information are we going to use to correct for the state? So if we set this correction factor to be 0, it means that we don't correct at all and we get back this ballistic approach. But if we set the correction factor to be, let's say, 1, then we would get this approach where we at each point completely accept what the measurement says. So this is quite literally an intermediary between those two approaches. So this is the sort of white box implicit paradigm, this is kind of the black box implicit paradigm, and this is sort of the gray box implicit paradigm. So let's talk for a second about this concept of state filtering. What does that actually mean? So state filtering is described sometimes as answering the question, what is the state x at some time k, given measurements up to and including time k. And in the stochastic formulation which we use, this is sort of dealing with probabilities and uncertainties, because we accept the fact that our model is not perfect, and therefore there is no exact solution to what the state should be. We are instead trying to find a state which is optimal in some statistical sense. And in Jastrzębski, which is one of the fundamental books to read on this topic, this is known as obtaining the filtering densities, so the probability densities. So we are now dealing with probability here. We have to sort of let go of the idea that we can find exact values for anything, but we have to contend with the fact that everything is uncertain. But that doesn't mean that we cannot estimate anything. We have to sort of estimate what is the most likely state at each time step. And as a side note, we can also just mention that in this framework of state estimation, at some given time k, if we use measurements from the future, so we are estimating at time k, and we use measurements from the future, then we call it smoothing. If we use information which is more than one time step behind us, then we will call it state prediction. But if we use exactly this middle case here, where we use measurements up to and including our current time, then we call it filtering. And the way we do this in practice is typically through some sort of recursive method, because we need to implement this in a computer eventually. We have to write a computer program to do all of this for us. And then it's useful to have some sort of recursive method for this. This is then a recursive implementation of this predict update step that I mentioned in the previous slide. In general, we can think of this as something called a recursive Bayes filter, if you want the sort of most general way of looking at this. But in practice, this is our famous Kalman filter, which I will assume is at least vaguely known to you. So, as mentioned, in order to do parameter estimation, we need to define an objective function. That is, we need to somehow quantify what it means for a model to be a good fit to our data. And as also mentioned, how we define this goodness of fit through the objective function is one of the things that separates different parameter estimation paradigms from each other. And here, for the purpose of this sort of Greybox modeling framework, the objective function of choice is going to be something we call the likelihood function. I'm sure that is something that you have at least heard of from statistics, but this is so important that we will go through this from the basics. So the definition of a likelihood function, which we denominate with a capital L, is the probability of some sequence of measurements y, capital N, where this brackets means that this is a sequence of measurements, of capital N measurements, given that we have a known parameter set and a known model structure. And again, from now on, I will omit this model structure unless I really need it to be explicit, but for the most of these derivations, just assume that the model structure is known, but I don't write it explicitly just to keep the equations shorter. But the informal interpretation of this likelihood function, this probability or this joint probability distribution, as we will see, is that this is the probability of observing a sequence of measurements. We have a sequence of measurements. We have made measurements over some time with a given time interval, discrete time measurements. And we want to calculate what is the probability that all of these measurements were generated by a system that can be modeled with the model structure M and parameters theta. That is the informal interpretation of what this mathematical identity here really is. But since this is a sequence of measurements, we can start to work on this likelihood function in order to sort of derive something that we can actually eventually compute by applying this so-called product rule, which says that the joint probability of A and B is probability of A given B times probability given B. To relate that to sequence of measurements means that we calculate something like this here. So we are going to now calculate this joint probability by taking these conditional densities, saying that first we assume that we know the probability of measuring y0, that's the initial measurement. And then we want to calculate the probability of measuring our measurement 1, given that we have already measured 0, or y0. And then we are going to multiply in the probability of measuring y2, given that we have already measured y0 and y1. And then we will multiply that again by the conditional probability of measuring y3, given that we have already measured the sequence y0, 1, and 2. And so on, all the way up until we have measured the probability, or we calculate the probability of having measured y of or y capital N, given all of the measurements from 0 to y capital N minus 1. And all the time also, of course, conditioning on knowing theta. So we keep these parameters as constant, and we work on the probabilities of obtaining these measurements. If this is difficult to sort of understand, that's perfectly okay. This is complex mathematics, complex concepts to really understand. And then I would suggest to look at some of the seminal papers within this field. For example, this Christensen-Madsen 2004, which I have references to on some of the slides. Or indeed sort of general textbooks on notion of probability will be useful to you in order to understand and accept that this derivation really is a natural evolution of this joint probability of a sequence of measurements. And assuming now that we can somehow calculate this beast of an equation down here, we have then an expression for the likelihood function for our dynamic system model for a given parameter vector. And then we can use some sort of algorithm to maximize this probability. So we want, in the beginning at least, to find the parameter vector theta, which gives the highest possible probability here. So this is sort of a probability-like, it's not really a probability distribution because it doesn't integrate to 1, but it is sort of a probability-like equation. And we want to find the parameter vector theta, which gives us the highest possible probability of obtaining the sequence of measurements. Unfortunately, although this seems sort of nice, this expression, assuming that we can calculate these probabilities, it's just multiplying stuff together, and there you go, that's your likelihood function. Unfortunately, it's not so trivial, because these conditional densities here are in general difficult or impossible to obtain. It's possible to show that for sort of a stochastic dynamic system we have to solve something called the Kolmogorov's forward equation in order to obtain these. And in general that's not really feasible to do. It's either not possible or numerically difficult. But since we have, fortunately, one might say, discovered that it's reasonable to model this diffusion term, which is really where our problems are coming from, as a normal distribution. It's driven by a Wiener process. Then we can actually model these densities as normal distributed. So this expression here might look a bit complicated, but if you analyze it, you might recognize that this is simply the multivariate normal distribution expression. It's quite well known from sort of lower level statistics classes, I would assume. So under the assumption that we have this normal distributed uncertainty in the state transition, the diffusion term, we can compute these densities using this expression. And to evaluate this expression here, it's really only two quantities that we need to compute. We need to calculate this E and this matrix here, epsilon. This is a vector, this is a matrix. And to do that, we can use a state filtering method, specifically a Kalman filter. And inside the Kalman filter, as you may be sort of recognizing just looking at the equations, we always calculate sort of a predicted one step ahead measurements. That is, we calculate what our best guess measurement for our model is one step ahead based on all the information up to our current time. This can also be formulated using this expectation operator. So that's the expected measurements one time step ahead. And then as part of the update step in the Kalman filter, we introduce our measurement from time k, and we compare that to the predicted measurement. This gives us something called the innovation process, which is this lower e here. And we use this notation e at time k, given information up to and including k minus 1. So that's what this notation here means. And then finally we need the variance, or the covariance of this term here, which is basically then the expectation of this expression here, the vector multiplied by the transpose of itself. That's going to be sort of a covariance matrix of this innovation process. And this is actually one of the key steps in the Kalman filter, that we need this equation here in order to calculate the Kalman gain. So all Kalman filters have some form of expression that gives us this innovation process and the innovation covariance, because they are needed to calculate the Kalman gain. I won't go into too much details on the Kalman filters, because I will assume that those are known. Otherwise, I would recommend this, for example, Optimal Estimation book by Dan Simon to study those in detail. That's going to be necessary to understand Kalman filtering in order to understand this approach to parameter estimation. Suffice here to say that the Kalman filter in its most basic form, which is for linear models, which is known to be optimal in the case of linear models with additive normal distributed noise. If you happen to be so lucky to be working with a model that is linear, of course, then you can use the basic linear Kalman filter. But for most realistic models aren't really linear. Most interesting problems are non-linear. And therefore we need different adaptations of the Kalman filter that can approximate the Kalman filter solution, the state estimation solution, also for nonlinear models. In general, we have three sort of main types of Kalman filter approximations. We have the extended Kalman filter, which uses this Jacobians in order to obtain some sort of approximation to the linear case by calculating Jacobians around some operating point. We have something called the unscented Kalman filter, which instead uses the sigma transform, calculating sigma points through Cholesky decomposition of covariances and so on, and then uses those sigma points to approximate these state transition distributions instead. Or we can use the ensemble Kalman filter, which is actually kind of a Markov Chain Monte Carlo solution to this solving of the Kolmogorov-Forward equation, which is the fundamental driving force of the stochastic dynamic systems. So all of these three formulations of Kalman filtering are applicable to nonlinear systems. One interesting special case is models that are non-differentiable, in which case the extended Kalman filter is sort of out of the question, because we cannot evaluate the Jacobians anymore. And one particularly interesting case of that is if the model itself is not really a mathematical function that we can really evaluate, but it could be something like a simulator. I did some projects in my PhD where I modeled thermal behavior of a building using electric circuit analogies. And then I used in circuit simulator as my model. So I just described the circuits, the very, of course, basic RC circuits in a circuit simulator. And then I treated my model as, or I used that simulator as the model. And in that case, there's no way I can take the derivative of that, because it's a piece of software. It's just a black box, but it does describe the state transition and the measurement equations. And therefore I can use that together with the unscented Kalman filter or the ensemble Kalman filter, both of which only requires the, let's see, where is it here, state transition and the measurement equation. So there's no requirements to actually having those explicitly defined. It's perfectly okay if those are just some sort of algorithm that we don't really see or know anything about. It can be a completely black box. And using the unscented and ensemble Kalman filter, we can still make this work and calculate the likelihood function for the parameters of a piece of software. And the final case here is where we have a very large state space, for example, for the reservoir models or hydrology models, maybe meteorological models, where you can have a state vector which is thousands, maybe hundreds of thousands of states. then you need to resort to this ensemble Kalman filter. It's actually what this framework is designed for. It's this very large state spaces. I just want to mention that there are also other ways to approach this, which is not based on Kalman filtering. For example, there is something called the particle filter, which is an even more general solution to this recursive base filtering, which can also produce these quantities that we need to evaluate our likelihood function. There are literature explaining how that is done. And there is also a number of sort of hybrid solutions. The Kalman filter turns out to be a very important algorithm for many different types of projects, and naturally, therefore, there is a lot of variations of this out there. So choose whatever Kalman filter approximation or version, particle filter maybe, that really suits your problem. That's the key to success here. So before we arrive at a final sort of expression that we can compute, there is one more important step which we have to apply, which is the log transform. There's really two reasons for this. One is just for simplification of numerical complexity. If you remember, this multivariate normal distribution expression has an exponent function which we would like to eliminate, which we can do by log transform. But log transforming also has the added benefit that we transform this product of probabilities into a sum of log probabilities. And it is indeed numerically much more stable to work in log space than to work in actual probability space. And just as a sort of informal intuition on that, if you imagine a sequence of maybe hundreds or thousands of measurements, the probability of actually getting a specific sequence of many measurements one after another is going to be really low. It's going to be virtually zero probability that you get exactly that measurement sequence. It's just that for some parameter vectors, you're going to be slightly further away from zero. And slightly can be a very small number. And dealing with very small numbers in computers is challenging because computers have finite precision. And therefore it's much more beneficial to work with this in log space, where we sort of completely get around this problem of numerical precision. So the final step in deriving our likelihood-based objective function is that we define this symbol here, which is like a lowercase curly l, to mean that we take the logarithm of our likelihood function, but for simplicity we will also multiply with -2. So multiplying with -2 has the effect of eliminating more elements of this multivariate normal expression. And just as a note, that before we were interested in maximizing probabilities, but since we now have multiplied by -2, we now have to minimize the log probabilities because we invert the problem. So that's why in the beginning we said that we are looking for a minimization of the objective function. It's just a side effect from the eventual derivation here, that we want to minimize the log probability. And then we finally arrive at our objective function, which, as you may remember from previous slides, we will call g. And this is then basically the sum of this innovation vector, the vector of the innovations, transpose times the inverse of this innovation covariance times the innovation again, plus the logarithm of the determinant of this innovation covariance matrix. And then we sum this together for each of our measurements, so each of our time steps from time 1 to time n. We have to calculate this equation by running the Kalman filter through the whole set of measurements. And then summing everything together, we get our final objective function over here. So before we move on to looking at some more practical view on this algorithm, I want to also discuss a bit something called the posterior distribution. And before you think, oh no, yet another probability thing, the posterior distribution is related to the likelihood function, and I will explain in this slide exactly how that works. So first of all, the posterior distribution is important later on when we will talk about Bayesian inference or Bayesian-based estimation. But it's also used in the frequentist statistics interpretation, which we will see in a second what that means. So it turns out that in most estimation problems, when we want to estimate parameters, if you remember some slides back, we said that we will find the optimal value under the assumption that the parameters is subject to the constraints of a parameter space. But we didn't say where in the parameter space. We just say that there is some box in this parameter space where the parameters have to be inside. A box in the multidimensional sense, of course. But with the posterior distribution, what we can do is through this famous probability principle called Bayes' rule, we can actually add a probabilistic description of what we may know or think about our parameters prior to estimation, prior to looking at any data at all. And this turns out to be very useful, especially in engineering senses, where almost always it's the case that we have some intuition or some knowledge about what the parameters probably are before we start doing any sort of estimation. It's very rarely the case that the best we can do is to say that, okay, they are inside some bounds. But even if that is the case, those bounds can also be thought of as uniform bounded priors. So we'll get back to that later to show how that's done. But even bounded parameter space can be described as a prior. But it doesn't have to be. It can also be many, many other different mathematical functions over the parameter space, which turns out to be very useful. So in Bayes' rule, we have this likelihood function, which we are now become quite friendly with. And we multiply that with the prior distribution. And then we divide it with this factor under here, which is called the evidence. But as we will see later, this evidence is not a function of parameters, it's only a function of data, and therefore it's not really affecting the parameter estimation. So we can get rid of that annoying term under there. I will show that later how that looks like. And then we get, on the left hand side here, we get the posterior distribution. And informally we can think of the posterior distribution as the probability of a given parameter being correct given a set of measurements. And if you remember a few slides back, this is sort of the opposite of what we said with the likelihood function, that the likelihood function is the probability of observing a sequence of measurements given that we know what the parameters are. And since we are interested in estimating parameters, in many ways this posterior distribution is much more intuitive, because it's directly the probability of a certain parameter being correct or not. We will get back to this posterior distribution later, so we will see this again, but I want to just sort of mention it here. Some remarks on this is that in order to evaluate the posterior distribution, we need to evaluate the likelihood function first, which we still do with exactly the same approach as we did before, using Kalman filters and whatnot. And of course the posterior distribution can also be an objective function. We can multiply with the prior, divide by the evidence to get the posterior distribution and use that in order to optimize parameters instead. And if we do this using some form of optimization algorithm, so this argmax or argmean thing, we will get something called the maximum a posteriori point estimate, or the MAP. And that's very commonly done also in sort of traditional cybernetic sense, not just in the Bayesian sense, which we will come to later in this presentation. So like I just said, it's important in Bayesian inference, which we will discuss in a later slide. Since this evidence term is a constant, that is, it's only depending on data, it's not depending on whatever parameter we are trying to evaluate, we can typically eliminate it from the equation. And then we say that our objective function g of theta is given as this expression here. That is, we say g of theta equals to likelihood times prior. And this is not equal to the posterior distribution, but it is proportional to the posterior distribution, because we eliminated this 1 over evidence factor here, which is constant anyway. So for terms of optimization, it doesn't really influence our result at all. If the objective function is scaled by some number, it doesn't really change where the optimum is. That's why we can usually get away with this simple expression here, just the likelihood function that we used before, but multiplied by the priors. One further remark is that, of course, this log transform is also important here. We have exactly the same issues with numerical stability, that multiplying a bunch of probabilities that are near zero together is really a bad idea in a computer, because you will just end up with a garbage result or zero result. So we still need to apply this log transform. So as we did with the likelihood function, we will again multiply this posterior distribution with -2 and take the logarithm of it. And that looks like this. So we take this -2 times the log of g of theta, and then we get this weird L symbol again, but this time with the subscript p, which is nothing but this log likelihood -2 times the logarithm of the prior. So that's going to be our objective function if we want to work with the priors. This relatively simple expression here, where this is exactly the expression that we already evaluated before. And notice that if the priors are 1, that means if the probability of our parameters is 1 for all possible values, that means that we don't really have a prior. We don't know anything. All of the parameters are equally likely. If that's the case, then this log prior will be 0, and this whole term just falls out. Which means that any method which is designed to work on the prior distribution, or indeed the log prior distribution, can also be used on the likelihood function directly. The only thing is that we then implicitly assume that all of our priors is 1 for all possible values of our parameters. That's important later for discussing Markov Chain Monte Carlo methods, for example, that indeed all of these Bayesian methods that are designed to work on the posterior distribution, they also work perfectly fine on the likelihood function, only that we then implicitly assume this prior equal to 1, which is in Bayesian terms frowned upon, because it's almost never true that we don't know anything. But still, mathematically, it makes perfect sense. It's a perfectly valid approach. Yeah. A note here on the implementation of this method is that the logarithm of the prior is not depending on measurements, and therefore this sort of can be computed outside of this whole Kalman filter. There's no, we don't, this is not something we evaluate for every time step. This is something we evaluate once for each parameter that we wish to investigate. So we compute that outside this iterative Kalman filter business. Yeah, and one final interesting comment here is if we look at this expression here and use our imagination a little bit, we see that this function here, which is the log likelihood, this is actually a surface or a manifold. It's some sort of structure that exists in parameter space. It's a multi-dimensional surface in parameter space. And so is this -2 log prior. That's also a surface in parameter space. And by multiplying with the priors in sort of non-log space in Bayes rule, in the log space, what we actually do is we offset our log probability, log likelihood surface by the log prior surface. And that's a useful mental picture to keep in mind when we look at some results later for what these methods can actually do. One final comment on this very important topic of constructing objective functions is this, returning one last time to this ballistic simulation idea. So I mentioned in one of these slides with these three different approaches to parameter estimation, that it's a very common approach to simply simulate the model from time d0 to the end of our data, and then only after the model have been simulated we calculate the errors between simulation and our data points. And we call this the ballistic simulation approach, because just like throwing a ball in a ballistic trajectory, we only use information at the start of our data set in order to calculate this trajectory. And now that we have studied in depth how a proper stochastic parameter estimation framework works, we can look at this formulation here, which is what we typically use when we do the ballistic simulation approach, which is that we have our model up here, and then we have our measurements here with the noise ascribed only to the measurements. There is no uncertainty in the state transition equation here, which is why we can do the ballistic simulation, because we know, if we know the state at time 0, we can calculate the state at time 1, state at time 2, time 3, up to time n, because there's no uncertainty. But looking at this stochastic differential equation formulation of state transition, we see that what we actually do when we perform a ballistic simulation model fitting is that we completely neglect the diffusion term. We neglect any uncertainty that might exist on our state transition. So hence we can argue that doing this deterministic approach or the ballistic simulation approach actually implies or implicitly assumes that our model is perfect. And everyone who works with models knows that that isn't true. We always have to apply some sort of simplifications or assumptions in our modeling. And therefore models are always wrong. George Box said something like this, that all models are wrong but some are useful. And this is why I would like to argue that this Greybox methodology is actually a more general approach, because it allows us to be at least conscientious about if we choose to neglect the diffusion term. We, after going through all of this mathematical shenanigans to understand how to estimate parameters for something like this, we are now at least aware of what we are doing. That if we use the ballistic approach, we know that this implicitly assumes that our model is perfect, and therefore we will only even think of attempting something like this ballistic approach if our model is at least very, very good. If we have a model with significant uncertainty attached to it, we really have to go through the proper stochastic Greybox framework. So now we have gone through all of the mathematics necessary for constructing our objective function. And just to sort of tie everything together, I want to try to present this in a slightly less theoretical way and more sort of an algorithmic overview of how this works, because this is something I know people very often confuse, because there is many aspects to this, there is many sort of loops involved. So I try to come up with a figure which explains this a bit more concretely, I guess. So, as we have said, what we are going to do is use a Kalman filter in order to compute this expression, that's the log likelihood expression, at each and every time step through our data set. So we have a set of data with n samples, and we are going to run this Kalman filter through that data set and calculate the innovations and the innovation covariance at each and every measurement, each and every time step. And we are going to do that under the assumption that we know the parameter and that this parameter is constant. It does not change while we run the Kalman filter. It's a constant for this part of the algorithm. So that's the loop which we have over here. We see that k goes from 0 to n, k equal to k plus 1. We do the prediction update, prediction update, prediction update through our entire data set. And only when this is finished, we return this objective function, which is the sum of this log likelihood expression at each and every time step. And this objective function is then returned to some type of optimization algorithm, which can then provide us with another guess for what the parameters might be. And then we again run the Kalman filter over the whole data set but this time with a different parameter. So now theta has changed. Now we have theta I instead of, so we start with theta 0, then we do theta 1, run the Kalman filter, return the likelihood function, then we guess theta 2, we go to Kalman filter, we run through the data set, calculate the likelihood function, or the log likelihood function, then we guess another parameter, and so on. So we have an optimization loop, and we have a Kalman filter loop. And for every parameter that the optimization loop suggests, we have to run the Kalman filter loop over the entire data set. And then, of course, at some point, based on some criteria which we usually define in the optimization algorithm, we will eventually reach some type of maximum here, based on this numerical optimization scheme that we choose here. I won't go into too much details what numerical optimization is. I will assume that it's sort of known at this point. But just to sort of get the idea through, what we are talking about here is that we want to have a method that, based on some initial guess what the parameters might be, we do the evaluation, calculate the likelihood function, and then we need an algorithm to guess which parameter should we try next, and then again calculating likelihood, and then again the algorithm needs to tell us, okay, now what, which should we try for the second iteration, third, fourth, fifth, 10,000th iteration. Who knows how many iterations we have to do before the algorithm is satisfied. And typically we do this with some form of gradient descent. It can be based on the simplex, trust region, etc. There is a whole army of different type of gradient descent or numerical optimization methods that we can use. The important thing for our purpose is that we need something which is gradient free, or we could do sort of a numerical gradient computation, but since our objective function is not a simple mathematical expression, it's actually a function, an algorithm which runs the Kalman filter through a whole set of data. It's not really possible to calculate the gradient of that. You cannot calculate the derivative of a Kalman filter in any sort of straightforward way. So we need a numerical optimization method which is gradient free. That's sort of the easiest thing to do. There are ways which you can then use numerical approximations to find the gradient, but that just means sort of numerically calculating the gradient yourself, which is actually what these gradient-free optimization methods usually do internally anyway. They tend to calculate some kind of numerical gradient approximation. So it's better to just choose something which was designed by an expert in numerical optimization to be gradient-free. So very simply, the way this works is that we start with some initial guess, let's say parameter theta 1. Then we calculate this point up here, but we don't really know the gradient of this. And then we calculate one more, the algorithm somehow does a jump. Maybe we are lucky and it jumps in the right direction, so we go down here. We calculate then theta 2. And then we know that since theta 1 was up here, theta 2 now is lower, has a lower value for the log likelihood, and therefore it's better. So we now start to have an idea that maybe we should continue in this direction. And if we do that, we come down here and we find this theta 3, which is again better. So maybe we do another jump, still going further right, because that worked well for the first two iterations. Maybe we end up over here. Now this increased a little bit again. And then at some point we will then end up in the bottom here, which is in the optimal point. So since this is gradient free, we don't really have this information represented by these blue lines here, which is the gradient. This have to be sort of implicitly calculated from just doing a lot of point estimates of the objective function. But internally, these optimization algorithms tend to have some representation of the gradient anyway. So it will sort of find its way down to the bottom of this log likelihood if we are fortunate enough that our log likelihood function looks something like this. I mean, if the log likelihood function has a clearly defined minima, that's not always the case. So if we happen to have a problem which is well behaved, then numerical optimization will find this optimum point for us, which is where our maximum likelihood parameter estimate will be. So to summarize this idea of maximum likelihood estimation, all of this mathematical and algorithmic framework which we now have gone through, including the Kalman filters, the log transformations, the definition of likelihoods, choice of Kalman filters, numerical optimization, putting everything together into this double looped algorithm, all of that is actually a very elegant framework for parameter estimation. Once we put all of this together, it's extremely powerful. And we can include the priors even to have previous information and so on. There's a very flexible, very powerful framework for doing parameter estimation. And most importantly, it has a very solid mathematical basis. So we use this probability concepts of likelihood and posterior distributions. And this use of these concepts from statistics allows us to do very useful or gives us very useful tools for analyzing and understanding the problem of parameter estimation in a more sort of rigorous mathematical framework, which we will see for the remainder of this presentation why that is beneficial. Using numerical optimization gives us this point estimate. As we saw in the previous slide, we find one point, which is the optimal parameter, the optimal or the maximum likelihood parameter estimate in some in that specific sense. But we can also use, as we will discuss later, something called the Hessian matrix in order to calculate some confidence bounds in addition to this point estimate. So this has, as I said, the attractive features of being a solid mathematical framework and providing us with a lot of diagnostic tools for model validation and also for model selection. But the main challenge of this framework is that it is mathematically complex. It requires that we use this state estimation, sort of Kalman filter approach, which is computationally heavy and sort of many layers of complexity in order to get this to work properly. But perhaps the most important challenge with using the framework that we have discussed so far is if we have a likelihood or a posterior distribution which is multimodal, something that has multiple minima. Then this notion of a point estimate, to say that our parameter estimate is one specific value, that sort of falls a bit apart. You can imagine that the likelihood function could even be sort of flat, that there is a whole segment where all parameter values are equally good, they have the same log likelihood. And then in that case, doing a point estimate with a numerical optimization algorithm kind of falls apart, because you have no way of distinguishing one estimate from another within that region, and therefore it's unreasonable to just give one value and say this is the optimal estimate, when another estimate in the neighboring region could be equally good. But this is fortunately something we can deal with, so we will get back to this specific problem in future slides. So one way of improving this approach further, I would say, is to replace the idea of numerical optimization with something called Markov Chain Monte Carlo methods. And this then fringes into this discussion of Bayesian versus Frequentist statistical perspectives, which is a very interesting topic for sure, but not something I really want to go into for this presentation, which I think will be already long enough. But for those who are interested in understanding the intricacies of Bayesian inference, I really recommend to look at these differences between the frequentist interpretation of statistics versus the Bayesian interpretation of probabilities and statistics. But for the purpose of this talk, or this application of Greybox parameter estimation to stochastic dynamic models, suffice to say that MCMC methods is an alternative to using numerical optimization. And MCMC is a whole sort of class of methods, which there are many different variations, like the Metropolis or the Metropolis-Hastings algorithm, and the much newer Hamiltonian MC methods. All of this is examples of MCMC, and there is also many other different versions of this. So the similarities between the MCMC class of methods and the maximum likelihood estimators or the maximum a posteriori estimators that we have discussed so far is that they use, at least for the dynamic system case, they use the same model definition, these stochastic dynamic system models. And therefore we have the same posterior distribution that we evaluate. We have the same description of what a good fit for a particular parameter means. And remember that I said before that the priors could sometimes be 1, and then the log probability becomes 0, and then we are left only with the log likelihood function. So it means that anything that can operate on a posterior distribution can also operate on a likelihood function, only under the assumption that the priors are 1 for all parameters. And since we then use the same likelihood function as before, it means that we still need to use the Kalman filter in order to evaluate the likelihood function. So actually, when we take the step from numerical optimization into the world of MCMC, nothing really changes with how we evaluate the likelihood function. Only two things are really different. Number one is that we use another type of algorithm in order to guess these parameters. So when we go from theta 1 to theta 2 to theta 3 looking for the optimal parameter vector, it's not numerical optimization anymore, it's something else, which we will show in the next slide what that really is. But also that we, because we are now in the Bayesian world, we have to think more carefully about this notion of priors, that we really don't want to accept that the priors equal to 1 for all parameters and that we don't know anything about our parameters prior to estimation. So it sort of comes with this concept of Bayesian statistics that we would like to treat the priors as meaningful information. So we put some extra emphasis into coming up with reasonable prior distributions for our parameters. But that's more for philosophical reasons, because we are now doing Bayesian inference rather than frequentist estimation, than out of mathematical necessity. As mentioned repeatedly, it's perfectly possible to do MCMC on log likelihood and implicitly assume priors equal to 1. The main differences between the MCMC class or MCMC approach and what we have discussed so far is that we use this stochastic search for optimal parameters. We don't do any gradient descent anymore, but we do a different approach to searching through parameter space in order to find our resulting parameter estimates. And I deliberately said resulting parameter estimates and not our optimal parameter, because that's one more important difference between the numerical optimization approach and the MCMC approach, is that we are no longer really looking for a point estimate. We are not interested in providing a particular value and saying that this is the value of the optimal parameter, because that's actually a suboptimal approach. Instead, we want a more complete picture of what our parameter space look like, and we want to calculate the actual posterior distribution of the parameters. And we want to represent this as a some sort of probability mass function, or probability density approximation, not point estimates. And that means that with this approach we can also deal with multimodal distributions, that is, distributions that have multiple local minima. And that is indeed a quite powerful extension of the framework discussed so far. So this MCMC algorithm is actually, when we look at this for the first time, I'm sure other people than me have thought that this is also, I mean, I thought that too, and I'm guessing other people thought the same, that this is really strange. Why don't we just do numerical optimization? Because that sort of makes sense, that you try to go to some optimum instead of this crazy jumping around stochastically like MCMC does. But it has some very nice properties. I won't go into too much detail again here, because then talk would be even longer. but I would refer you to relevant literature on MCMC methods, again of which there is a lot, and there is many good lectures around YouTube on MCMC methods themselves. But the key notion of MCMC I will try to explain. So I try to make a drawing here where we show a parameter space of 2 dimensions, and for some arbitrary reason we decided that our initial parameter guess is over here. And this ellipsis here is representing sort of the topological structure of our likelihood surface, which has one global optimum here and a local optimum over there. And the MCMC method works by making jumps, stochastic jumps. So from this point, which is then our, we will call it a candidate parameter, at step 0, we then make a jump to candidate number 1. And these jumps, they are made stochastically by drawing from a distribution which we call Q, or the proposal distribution. That is something we choose ourselves. There is some requirements on how we choose this Q. Typically it's some form of normal distribution with some specific covariance. But again, I refer you to the MCMC literature in order to learn more about how to choose good proposal distributions. But we make this random jump, and then we obtain a new candidate parameter over here. And once we have this new candidate, we evaluate it by calculating this log prior, which is exactly the same as what we did for numerical optimization. The log likelihood minus 2 times the log of the prior. But then from this log prior of our new candidate up here, we do a comparison with the log prior of the previous candidate, where we were before the jump. And then we calculate this difference here, so the log prior of the previous candidate minus the log prior of the new candidate. We divide by 2, take the exponent, and then we obtain this factor which we call alpha. And this factor is sort of the key to how MCMC methods work, at least on the base level. Because the whole idea here is that after we make this jump, we have to make a decision if we want to stay here, or if we want to stay, or if we want to stay where we were, or if we want to accept, as we say, this new candidate. And the way we make this choice is again through randomization, so some stochasticity involved here, where we treat this alpha as a threshold, and then we draw some random number between 0 and 1, so a scalar number between 0 and 1. And if this number is less than alpha, we will stay where we are. But if it's, no, sorry, if this number is less than alpha, we will accept the new candidate. If number is more than alpha, we will stay where we are. And if you look at this expression, we will see that since these are negative log likelihoods, if our new candidate is more negative than the old candidate in the log prior, that gives an alpha which is bigger than 1. And if alpha is bigger than 1, it means this acceptance criteria is always true. So this jumps, the new candidate will always be accepted if it happens to be better than the current candidate. So the new candidate is better than the current candidate, we always accept. But the real trick here is that there is also some chance that we might accept it even if the new candidate is worse than the old candidate. And that's actually what happens up here. So my MCMC algorithm here, which is of course totally artificial, was jumping around the global optimum here, and then for some reason decided to take a walk outside of this optimum. And using some sort of gradient descent approach, that wouldn't be possible because it would have to go against the topology of our likelihood function. But MCMC can do that because by some random chance we accept these jumps here even though they are worse than the previous candidates because of this probability test. Yeah, and also there is also the chance that we don't accept, of course, this candidate. So here we have the case where we try to make a jump up in this direction, which is probably worse than where we were to begin with here, because it's further away from the global optimum. And here this is not accepted. So here we try to go a jump here, and then we decided to stay because of this acceptance test, and then we made a jump here instead. And this is purely stochastic. It's purely a random chance involved here, how we traverse through this parameter space. And then it can be shown, which I will not do here, that because of these mechanisms, the jumps that we actually end up accepting is accepted with a probability that is proportional to the posterior distribution itself. So based on this chain of jumps, we can actually empirically approximate this posterior distribution. And that is where this power of MCMC comes in. But using this actually relatively simple algorithm, but which is still a bit alien until you get used to it, we can actually recover this posterior distribution, which is kind of the goal of parameter estimation in the Bayesian world, that we wish to find some approximation of this posterior distribution. So this is an example from a paper I wrote some years ago, where I used MCMC on a dynamic system, stochastic dynamic system model. And what we have on the left side here is a bunch of these chains, Markov chains of random jumps stacked on top of each other. So since one chain is proportional to the posterior distribution, having multiple chains and adding them together is also proportional to the posterior distribution. So very often we do sort of use computational parallelization in software to have more than one chain running at the same time. That's why we have different colors here. And from all of these chains, which then exist in this 5-dimensional parameter space, we can calculate histograms over pairs of parameters. And then we can compute these colorful distributions here. And this is actually something called marginal distributions. That is the empirical marginal distribution over our parameters. Again, please refer to relevant literature on MCMC and basic statistical theory to understand how or what a marginal distribution really is. But this is the output of an MCMC-based parameter estimation scheme, that we obtain these sort of histograms, which we can then represent using a heat map or a colorful plot like this, where the red color is representing the high probability regions. So this is a topological representation of this log posterior, or the posterior distribution surface. And this actually gives a lot of information about the parameter estimation problem. So we can see that, for example, here this is almost pure Gaussian. So this parameter and this parameter is actually quite independent of each other, whereas this one is sort of skewed. That tells us that this parameter here and this parameter here, they are highly interdependent. So based on this posterior distribution, we can actually extract a lot more information about our parameters than what we could if we were just given a point estimate, which will then be sort of the center of these red spots over here. So I'm only showing this then here to sort of highlight that specific point, that MCMC, although we have to then attend with some additional complexity in that the use of MCMC is slightly more complicated than just using numerical optimization. And we also have to deal with this notion of Bayesian inference in order to analyze the results. But the benefit of that is that we obtain a very informative view on our parameter estimation scheme. So this is actually a very, very powerful approach to parameter estimation. Of course, if we really wanted a point estimate, it's trivial to compute the map estimate out of something like this. It's just looking for the bin which has the highest probability density here. This is easy to do, but this is a more complete picture. Yeah, As a final thought in this segment, I want to just mention this again, this frequentist versus Bayesian interpretation of parameter estimation. It's not really of any huge practical relevance. If you're just interested in doing parameter estimation, this doesn't really concern you that much. But for those who are interested in really digging into this topic, I would recommend to do some studies into what this means, frequentist versus Bayesian parameter estimation. It's a very big topic, and it's actually somewhat contested. Some people even describe this as a war among statisticians. I wouldn't really take it that far, but it is at least, let's say, a topic of some debate. And in engineering in general, parameter estimation tends to be based on sort of a frequentist interpretation. We are looking for a point estimate with some confidence bounds around it. This is typically the sort of frequentist approach to parameter estimation. And we typically focus then on the likelihood function. The fundamental difference is really in the let's say the interpretation of probability. To a frequentist statistician, probability is just the fraction of favorable outcomes divided by the total outcomes, which is sort of, at least here in Norway, it's sort of high school probability. You flip a coin and you count how many heads you get divided by the number of total flips, and that's the probability of a head. Whereas in the Bayesian world, we take a slightly more sophisticated, I would say, view on probability as being a representation of degree of belief. So we say that if we have a probability of or a probability distribution over parameters, for example, that is not really saying anything about the frequency of how often we would expect these parameters to be estimated if we repeated the experiment, which is the underlying intuition of confidence intervals. But instead we say that this is our belief in how the parameters look like. So this is a distribution of belief over the parameter space. That is actually, in engineering terms, I would argue, a really useful perspective on this idea of parameter estimation. Yeah, and then of course this idea of introducing the priors, which is, you can do that in the frequentist sense as well, with the maximum likelihood estimation becoming maximum a posteriori estimation. But I would argue that in the Bayesian framework, because of how we view the priors as being sort of another, the log priors being sort of another surface or manifold in the parameter space, which warps the likelihood surface, it's a more useful perspective on the inclusion of priors available in the Bayesian setting. So now we come to the important topic of diagnostics and model selection comparison tools. I mentioned initially that one of the reasons why this likelihood-based stochastic dynamic model Greybox parameter estimation approach is so powerful is that we base everything on a statistical mathematical framework. And the use of this mathematical basis actually allows us to utilize existing statistics theory in order to both validate our estimated parameters and also compare different model structures. So for the remainder of this presentation, that's going to be the focus on these different tools that we can use in order to evaluate the parameter estimations. So far we discussed at length the different versions of parameter estimation, either the sort of frequentist approach with numerical optimization for point estimates, or the Bayesian MCMC approach. But now we are going to look into these other tools for model validation, model comparison, and also this topic of parameter identifiability. So the idea of model validation is that when we estimate parameters, we get a result usually, but we shouldn't implicitly trust this result, because it's just from the complexity of the algorithms and the mathematics involved, it's reasonable to assume that things can go wrong. Therefore, we need some kind of scheme framework in order to evaluate, validate our results. And one approach to doing this is again returning to this assumption of normal distributed innovation process, that we assume the diffusion term to be actually normal distributed. And if that is the case, and if our parameters are actually viable, correct in a sense, we would expect this innovation that we anyway have to calculate in order to evaluate the likelihood function to be normal distributed. So one approach to validating our models, actually to determine if the model is sufficient or adequate to describe the data that we have, is to look at these residuals and test them for being normal distributed. We should note here that this assumption of normality is actually used in the derivation. So this normality testing of residuals is actually a requirement to use this whole scheme, that we have to verify this assumption that the residuals and therefore the diffusion process is indeed normal distributed. So how do we do that? Again, this is something which I would refer you to the relevant literature on the field. There is a bunch of textbooks on statistics which also deals with how to test if something is normal distributed. For the purpose of parameter estimation, it's the sequence of the residuals, this lowercase e values, which we calculate in a Kalman filter, that we wish to perform normality tests on. But here I will just mention some of the approaches that is available. This is by no means an exhaustive list, but it is the ones that is, I guess, the most commonly used within this sort of parameter estimation framework. I think the most useful one and the easiest one to evaluate is something called the cumulative periodogram, which is actually the cumulative sum over frequencies for the power spectral density. And power spectral density is basically the frequency spectrum from the FFT squared. And then we make a cumulative sum over this, and then we normalize it so that the value at the highest frequency is 1 and that we start at 0. And if this residuals or the innovation process is actually normal distributed, it means that in frequency spectra all of the energy is evenly distributed across all frequencies, and therefore this cumulated PSD should then be a straight line. If it's not a straight line, it means that there is some part of the frequencies which has residual structure, and therefore it's not really normal distributed. And more sort of quantitative, straightforward test to this is the Kolmogorov-Smirnov criteria. But more interestingly, this Kolmogorov-Smirnov theorems can be used to compute bounds on this cumulative periodogram, so that rather than just doing sort of a qualitative analysis of this more or less straight line, we can define with some stated significance what it means for this line to be straight. So we set some bounds around the perfect straight line and say that if our cumulative periodogram is within these bounds, we will say that this is a normal distributed residuals with significance alpha. Another more sort of heuristic but still useful approach is something called zero crossing. If a set of data, in this case the innovation process from our Kalman filter, is truly zero mean random, it means that we would expect the values to change sign approximately half the time. So if we, for all of these values, take the value at time k, multiply it with the value at time k minus 1, that means that half the time the product of those two values should be negative and half the time it should be positive. Because if both values are negative, it's positive. Both values positive becomes positive. One positive, one negative, we get a negative result from this product. So it's a very simple way of calculating zero crossings. And then we can just count how many of those products are negative. And we expect that if this is a perfect normal distribution, about half of those products with one sample with the previous sample should then be negative if this is truly normal. It's possible to use the autocorrelation, of course, for normality testing, and also maybe the simplest approach is to just draw up a histogram over this innovation process and just visually inspect if this looks like a sort of a Gaussian bell curve. Then we can conclude that this is more or less normal distributed. But it's many approaches to this. The important is to find a usable approach. I would recommend this cumulative periodogram with the Kolmogorov-Smirnov confidence bounds in order to have an actual statistical test. But there are also other more advanced statistical tools in order to do normality testing. Another important topic when dealing with models, especially these Greybox models, which are often sort of simplified physical descriptions, is this model selection. So if we deal with simplified physical models, it means that something has been left out, that we have done some sort of strong approximations to the physics of the system that we are interested in. And that raises the question, what can we leave out, and how complex of a model is complex enough for the data set that we really have. And that is something which we can answer using model selection. So let's say that we have two models, M1 and M2, both of which have been parameter fitted, and the optimal value for theta 1 and theta 2 has been found. How do we determine which of those two models is better? And one way to approach this is using the so-called likelihood ratio test, which is derived from Wilks' theorem. And this says that if one model, let's say model 1, is a subset of the other, so that means model 2 is model 1 plus some complexity extension, then we can use this test together with the chi-square distribution in order to perform a statistical test of if this addition of complexity, making model 2 more complex than model 1, is really justified. And this looks something like this, saying that 2 ln to this likelihood function, or the likelihood ratio, that is equivalent to this expression here, using this log likelihood, and then testing the difference in log likelihood of the optimal parameter and model 2 versus the optimal parameter and model 1. And if the difference is bigger than this threshold here, then we will say that model 2 is the superior model and it's justified to add complexity. Chi-square has two parameters. One is the significance alpha and one is the degrees of freedom NDF. And here NDF is the difference in dimensions of parameter space. So by making model 2 more complex than model 1, we add additional parameters. And what we actually test here is if increasing the dimension of the parameter space is really worth it. If it improves the fit of the model so much that it's acceptable sacrifice to then have more complex model structures. And the significance of confidence level alpha is used to sort of adjust how sure we want to be that this conclusion is correct. It's sort of a hypothesis testing scenario, this. And the procedure then for constructing these models is that we start with sort of the simplest model structure that we deem reasonable. We fit the parameters to data, and then we extend the model by adding more complexity, and then we perform this likelihood ratio test in order to see if this additional complexity is justified. And we can do that in multiple steps until we reach a complexity where we can say that adding further complexity is not justified according to this likelihood ratio test. And then we sort of found our model complexity. Another topic which is very important when we discuss diagnostic information related to parameter estimation is this idea of quantifying uncertainty. So very often when we see people do parameter estimation in engineering, we only get one particular, so we get a scalar value for our parameters, we get the optimal estimate, but we don't really get any sense of how sure we are that this parameter is indeed the best solution. and what are the tolerances for our parameters. If, let's say, the optimal value is 1, could we also use 1.1, could we use 0.9, could use 0.5, and so on. And that's where this notion of quantifying uncertainty comes into play. So very often we have this scenario here where we just get sort of a point estimate. So we have some objective function, maybe a log likelihood function if we are lucky, and then we do numerical optimization, and we are lucky again, so we find this optimal point here, which is our maximum likelihood estimate. And then if we just supply this point estimate, that's sort of the minimum we can do. And that might be enough, depending on our task in engineering. Maybe that's all we need. But usually it's very convenient to also have some notion about how sure we are that this parameter estimate is the best, or is the real parameter that we are after. If this is some physical quantity, let's say the length or the mass of some physical object, then we would like to know how sure we are that this is correct. If we are estimating the mass of something, we say this is 5 kilograms, maybe it's really 7 or maybe it's 3. Depends on how good our model structures are, how good our data is. But if we have a confidence interval which says that the mass is between 4.5 and 5.5, for example, then we know that we are 95% confident that the value is between those two upper and lower bounds. So having a confidence interval is really a much more, let's say, it provides more information out of the parameter estimation scheme, which is why we should always try to use a method which can provide some sort of confidence bounds to estimates. Personally, I tend to be skeptical if I see estimates of anything without confidence bounds, because it means that whoever made the estimate is not really checking the result. I mean, it doesn't give enough information with just a point estimate. Ideally, we should expect at least a confidence bound. But the best case is if we have an actual distribution, like we discussed when we talked about Markov Chain Monte Carlo methods, that we prefer sort of a distribution, because that is the complete picture. That is the whole sort of perspective of how the likelihood or the log posterior function looks like over the parameter space. So that's the sort of the best case scenario. So we have the point estimate, the confidence interval, or the whole distribution, which is this shape here. So some notes on this confidence interval. And this is maybe a little bit besides the point, but I see that this notion of confidence intervals is so often misused that I think it's worth some special mention here. The definition of a confidence interval comes back to a paper by Neumann in 1937, where this is actually just a screenshot from his paper. So he postulates a confidence interval with an upper and lower bound and confidence alpha. And by his own definition, he says that if we assume that we perform an experiment and we estimate a parameter, and we say that with confidence 95%, this resulting parameter is between the lower and upper bound. That means that if we perform the experiment 100 times, 95 of those 100 times, this parameter would be in this interval. That's what a confidence interval means. It's a strictly frequentist definition of uncertainty. But carrying that definition a bit further, so let's say that we have done some experiment and we have calculated 95% confidence interval of 1 as the lower bound and 2 as the upper bound. What is then the probability that our parameter is actually in between that interval? And this is where people get confused when it comes to confidence intervals, because many people will say that, oh, this is 0.95 because it's a 95% confidence interval. But that's actually not the case, because confidence intervals is based on frequentist interpretation. And in the frequentist paradigm, once you have a parameter like this, this is already an estimated parameter. It's not a question of probability. So the probability of the parameter being in the interval is either 1 or 0. If the parameter is between 1 and 2, then the probability is 1. If it's not in the interval, then the probability is 0. So by Neumann's own words, the question of whether the true parameter is inside this interval or not isn't really a question of probability, because we have calculated the bounds as constant values. They are not random variables, and the true parameter is also not a random variable. And therefore we cannot make any sort of probabilistic statements about this variable in the frequentist sense. Remember that in the frequentist sense we treat the parameters as a known. It's the measurements that are the random variables. However, in the Bayesian terminology, when we flip this around, then this becomes a very different problem. But then we don't deal with confidence intervals anymore. Then we deal with probability distributions, which is a different thing. Yeah, and this notion of confidence intervals was clarified a bit more by Simon Kullback in 1938, where he says exactly this idea that if you have a confidence interval with confidence 95%, it means that prior to creating this interval, you have a 95% probability of the interval being correct. Meaning that if you perform the experiment 100 times, 95 of those times will give you a confidence interval that actually captures the true parameter. So it's not a statement on any individual confidence interval, it's the expectation of the interval being correct before you actually do anything. That's what confidence levels are. And then by extension, if you repeat the experiment 100 times, you would capture the true parameter alpha % of those times. Yeah, so we should not confuse 95% confidence interval with a 0.95 probability region. It's actually a side note for what I'm talking about for the most of this video, but still it's an important thing to be aware of, not to abuse the notion of confidence intervals. So how can we in a reasonable way express the uncertainty of the estimated parameters that we have? So in general, we could define a region in parameter space where this objective function g of theta differs from some optimum g of theta hat by less than a threshold. So formally we define a set of parameters theta where this difference is less than some threshold. And this set, of course, is a subset of the whole parameter space. And now the different ways we can express uncertainty really comes down to how do we define this difference and how do we choose this threshold. One very common approach is to use an elliptic region. That's actually just a multivariate confidence bound. Becomes sort of this elliptic regions here. It's just the idea of a confidence interval extended into multiple dimensions. And indeed, in one dimension, this reduces to a regular confidence interval. But here we have these elliptic regions, which is defined as any parameter minus the optimal parameter multiplied by this covariance matrix inverse, and then multiplied again by this difference, which is less than a threshold. And we use again our chi-square distribution to calculate the threshold. And this sigma inverse is given by the Hessian, which I mentioned earlier. That we can use the Hessian to calculate confidence bounds. Just note that when I talk about elliptic here, it doesn't necessarily mean ellipses in 2D. It can be elliptic in n dimensions. So it's sort of a super ellipse in a way. Yeah, but we can use the Hessian on this form, which is the sort of second derivative of the log likelihood function, to calculate this matrix here, sigma inverse. And then we can find this region here, which is relatively straightforward to compute. And then we can get some sort of representation of the uncertainty, but this is then based on an assumption of elliptic regions. And naturally, the reason we use this assumption is because in the case of normal distributed uncertainty on our parameter estimates, then this is exact. So if the log likelihood, or if the likelihood function is a normal distribution over the parameters, then this becomes sort of an exact representation of that distribution. But another approach, which is more general, let's say, is to avoid this assumption of elliptic regions, basically avoiding the assumption of a normal distributed parameter space, because that is very often not the case. Even though the model assumes normal distributed diffusion term, that does not mean that the parameter space itself or the likelihood function is normal distributed. So instead we use the same Wilks theorem that we used for model selection. Same logic applies here, saying that with respect to an optimum parameter value, that's the maximum likelihood estimate, and the log likelihood of that parameter, any parameter whose log likelihood differs from this optimal estimate by less than the threshold delta alpha is said to be within the confidence region. This is called an asymptotic confidence region. So it relates to this likelihood ratio test as follows, that we calculate this as our sort of initial model and this as our extended model. And then we try to find out what region of theta this statement here is true, and that's what gives us our confidence region. So the final topic, I think, for this video is going to be on parameter identifiability. The concept of parameter identifiability comes from the realization that when we do parameter estimation, we are of course looking for some unknown, and it's natural to think that this process of estimating an unknown parameter might not always work. It's possible that this estimation can completely fail. There are parameters, or there are situations where parameter estimation isn't possible. And understanding this concept of identifiability is basically the art of trying to figure out under what conditions parameters are possible to estimate. That's what we mean by identifiability. When are parameters possible to estimate equals when they are identifiable. And there are basically two requirements that we have to account for when we look at parameter identifiability. Number one, we need a model structure which is of such a form that its parameters can be estimated. There are many possible model structures which have parameters that are not possible to estimate. And the second thing is that we need the data set to be informative enough that it contains the sufficient information that we can estimate parameters. And in both of these cases, what this comes back to is that if the objective function, which is sort of a combination of both simulating the model structure with some parameters and comparing those to data, if for whatever reason this objective function is insensitive to changes in the parameters, that makes those parameters non-identifiable. And that can happen for one of these two reasons. Either the model structure is not affected by changes in parameter, or the data is not, or the simulated output of the model is not affected by, with respect to measurements, is not affected by the change in parameters. To exemplify this a little bit, this first kind of non-identifiability is known as structural identifiability. That is, if the parameters are identifiable from point of view of the model structure. So if we have a very simple and stupid model like this, which says that the state transition is a plus b multiplied by the state, I guess this is pretty clear that this is not identifiable, because any value for a can be compensated for a value by b. You could only identify the sum of a and b. You would not be able to find any values for a or b, because a can have any value, because you can always find a value for b, which still makes the sum a plus b be whatever you want. This is sort of a case where the parameters are non-identifiable because they are sort of closely related. Another, perhaps even more obvious case is if you have a model structure like this, that for some reason there is a 0 multiplying one of your parameters, then clearly whatever value you choose for b here is going to be fine, because it's no way that b here can affect anything. It's multiplied by 0, so it just cancels out. And then b can take basically any value, and therefore it's non-identifiable. So these two examples are sort of super trivial. In reality, it's never this easy to see what is and is not structurally identifiable. So we need a diagnostic tool in order to test for structural identifiability, which we will come back to in the next slide. This second form of identifiability problems, which relates to the data set rather than the model structure, is something we call practical identifiability. And the example of this would be, let's say that we have a model of a pendulum and we perform an experiment with the pendulum, and we expect to find the mass and the length of the pendulum based on this experiment. Now, if the pendulum is completely stationary throughout our experiment, so it does not move, then clearly this data is just going to be a flat line. And this flat line is not really informative about the parameters of this pendulum. No matter what the mass is and the length is, if the pendulum is stationary, the angle is still going to be 0, no matter what the mass and the length is. So if the pendulum is small, large, medium, it's not really detectable from just looking at the data, which is just 0 all the time. So this is sort of an extreme case of practical identifiability, which again is super trivial, but it still shows the point that there are cases where your data is not informative as to the dynamic behavior of the system you are trying to analyze or trying to estimate parameters from. And then you get this problem with practical identifiability. There are quite a few approaches to trying to investigate this notion of structural identifiability that has been dealt with quite extensively in the literature, much less so with the practical identifiability, because it's slightly more difficult to get to grips with. There are some different tests one can do to look at dynamic information content and so on. But one of the methods which sort of deals with both of these concepts in an elegant way is something called the profile likelihood. And since we are anyway dealing here with likelihood functions, this idea of profile likelihood is also very suitable to our framework. And it's actually pretty simple to understand, because we have already studied at length how to optimize parameters for this log likelihood function. And in order to test for identifiability using the profile likelihood method, the only change we do to our method is that we do this optimization of parameters in 2 steps. So we take one of the parameters and we keep that out of the optimization problem. So we choose some parameter and we choose a constant value for that parameter, and then we optimize all the others. And then we get some sort of optimal log likelihood, given that this parameter that was kept out has a known value. But then we repeat that process for multiple known values of that parameter. We can either choose this using some sort of gradient descent in addition to the numerical optimization tool which we use for the remaining parameters, or we can just do a brute force like a grid across this parameter that was left out of the optimization problem. Yeah. And the reason why this is very useful is because we can again utilize this Wilks theorem and this notion of likelihood-based confidence regions or asymptotic confidence intervals. And we can say that when we choose a bunch of values for this parameter that's left out, and then we calculate the optimum for all the rest, we can get a shape like this. And then if we add threshold here using the chi-square distribution, we can say that if it is possible, based on this profile, calculating the likelihood for the optimal likelihood for all but one parameter, where the last parameter has a known value. So a known value here, all across this axis. If we, in the resulting profile, is able to place this chi-square threshold such that it gives us a bounded interval where we can say with significance alpha that the parameter has to be in that interval, then we say that the parameter is identifiable. Basically, it means that if the confidence interval exists and is bounded on both sides, then we deem that parameter to be identifiable. If it happens that it is not identifiable, but that this profile still exhibits some kind of minima, then this is said to indicate that we have a practically non-identifiable problem. It is an optimum, so we could calculate sort of a maximum likelihood value for it here, but we cannot place this bounds on it. There is no way that we can compute a confidence interval at the desired level of confidence, and therefore we cannot say that this parameter is identified. It's sort of missing an upper bound here. We don't know what the parameter is. We can find a value, but it doesn't mean anything unless we can place a bound on it. And the final case is if we have something like this, where this likelihood profile simply fades off into one direction and there is no clear minima anywhere, then this is said to indicate structural non-identifiability. And I would recommend looking at papers by Raue, 2008 and 14, if memory serves. Has a very good discussions on profile likelihood. This concept of profile likelihood can also be extended into 2 dimensions, which is something I worked on in my PhD work in one of my papers. We go through how this notion of profile likelihood can be extended into 2 dimensions. And the way we do that is very simple, that instead of holding out one parameter, we simply hold out 2 parameters, and then we optimize the rest. And we can show that while the normal one-dimensional likelihood is equivalent of projecting this likelihood hypersurface from parameter space onto one of the parameters, doing the 2-dimensional approach projects the same log likelihood surface onto a plane of 2 parameters. So we define a plane of the parameters I and j, and we project this multi-dimensional log likelihood surface into a 2-dimensional plane, which we can then draw using sort of a heat map where color represents the elevation in the sort of the z direction here. Yeah, and the reason why this is very useful is because we can then get a much better visualization of how the likelihood function really looks like. So the information in these 2 plots is the same as the information in this plot, only that this plot here is this shape projected in that direction, and this plot is this shape here projected in that direction. The downside of this approach is that it is very computationally heavy, because where the normal one-dimensional profile likelihood requires simply to sample one of the parameters and then optimize the rest, this approach requires us to sample over 2 parameters. So we have to make a grid here of values of these parameters. And it's typically the better your result you want, the finer pitch this grid has to be. And if here you have a grid of 200, then you might want 200 by 200, which is then of course sort of 40,000 repeated optimizations you have to do of the remaining parameters. And the complexity pretty quickly explodes when you also have to do this onto each possible plane of your combination of parameters. So if you have more than, let's say, 5-6 parameters in a model, this very quickly becomes infeasible to do this 2-dimensional approach. But it's possible to do the 1-dimensional approach because that's linear in the dimension of your parameter space, and then only do the 2-dimension approach if you have particular parameters, combinations that you want to investigate further. Looking at this figure here, I wanted also to add a comment on this notion of priors, which I have discussed before. So one thing which is actually very nice with this two-dimensional projection profile likelihood approach is that rather than this shapes here, which is not so easy to understand why there's a sharp bend in this one-dimensional profile here, once we do the two-dimensional profile, it's very clear that there is some sort of surface going on here, which has been cut off at the value 0.17 for both parameters. And we can sort of envision that this shape should actually continue in this direction. That's much more easy to visualize when we have these 2D plots. But what is actually happening here is that we have a bounded parameter space. So we have a parameter estimation problem subject to the constraints of a parameter space. And it's interesting to note that in this discussion we had previously about the posterior distribution and the inclusion of a log prior as kind of a reshaping or an offset to the likelihood surface. We can say that adding bounds is actually equivalent to introducing a uniform but bounded prior. So a prior which has a constant within some interval between theta min and theta max. That's the same as adding a bound. And doing that and taking the log of this thing, we would see that outside this bound, the log of this would be basically minus infinity. So if we take our log surface, which should log likelihood surface, which should actually have extended out here, but we say that anything outside this region here is actually offset by minus infinity. That's the equivalent of just basically cutting off this log likelihood surface at the bounds of our initial parameter space. So taking this view of log priors as an offset by another surface, offsetting our log likelihood surface by another surface, this sort of helps to visualize what is actually happening here, that we offset part of the log likelihood surface by minus infinity, and therefore it sort of disappears. A further comment on this idea of profile likelihood is that, as you may have already noticed, this results from both the one- and two-dimensional profile likelihood method is actually quite similar to what we showed before for the MCMC method. That's actually an important observation. This is also from one of my papers where we did some parameter estimation on a model, and we tried to do that with both using the profile likelihood approach and the MCMC approach. And as you can see here, both in the one-dimensional case and the two-dimensional case, the results we obtain is very similar. And that's actually shouldn't be a surprise, because in both cases it is the same surface that we are investigating. We are looking at the log likelihood hypersurface, only that we are visualizing it either in one parameter or in two parameter perspective. But there is a significant difference here, because when we do a profile likelihood method, you remember that profile likelihood method actually keeps one parameter constant or two parameter constant and then optimizes the rest. And optimization in that sense is equivalent to maximization. So when we do the profile method, we are looking for the maximum. But when we do the MCMC and then calculate these shapes which we have here, this is actually something called marginalization. It means that we calculate the histogram and we then calculate the sum over some sort of subspace direction inside the parameter space. So we define this plane of two parameters, and then along all possible normals of this parameter plane, we either calculate the maximum, which is the profiling methods, or we calculate the sum, which is the marginal distributions of MCMC. And in the case of more or less normal distributions, those two tends to be or are actually equivalent, except for that the profile methods, which is shown in red here and on the right here, they are deterministic, meaning that they, in a prescribed deterministic way, explore all of parameter space. So they are exhaustive, they will always find the global minima, they are guaranteed within the defined parameter space to find all possible minima. The downside being, of course, that this is very computationally expensive. But in difference, which is especially clear on these two-dimensional heat maps here, that the MCMC method is not deterministic. It is, as we showed, it's stochastic. It's jumping around in some sort of random way. And how it jumps and explores and how likely it is to visit different positions inside the parameter space is directly proportional to this posterior distribution. So for the regions of parameter space which has high posterior density, this equivalency is much stronger. But once we get to these outer edges here, we see that this MCMC is not really visiting these regions very often. If we had run these chains for much longer, this equivalency would become stronger and stronger. So in the limit of infinite sample size for our Markov chains, this MCMC method would tend towards these projections here, at least for the likelihood surfaces that are more or less normal. So one final comment on this equivalency, returning to where we discussed before, is that there are, of course, some cases where we have non-normal distributions, and especially where we have multimodal distributions or multimodal topologies or manifolds, log likelihood hypersurfaces in parameter space, where this equivalency sort of falls apart. And we have a particular example of this here, which one of my supervisors termed the case of the camel versus the dromedarius. So if we have something like this, where you have two humps like this, which have a lower peak than this third hump, if you try to make the projections of this against the y-axis, then we would determine that this is the optimum value. Projections would give us this red shape over here. So then we would say that this is the maximum, because we take the maximum here, we get this peak. We take the maximum here, we get this peak. However, if we were to do marginalization instead, which is the MCMC approach, we are not looking at the maximum, but we are instead summing over all of this. So then the value here would be sort of all of the probability mass along this sort of direction. Let's say we marginalize out x and we sum over x in order to compute the marginal density for y. And then we would conclude that in this case, this value of y, that is this value of y, would be the optimal, because there is more likelihood mass, let's say, for this value of y compared to this value of y, even though the log likelihood function is actually higher here. So there are cases where this difference between the marginal distributions of the MCMC differs from the sort of maximum value or the projections of the profile methods. Yeah, I think we will end the lecture there. I think it's quite a lot of information here to take in. There's a lot of topics that we have just sort of scratched the surface and touched on, which I guess recommend to study more on your own if that is of particular interest. But just to sort of sum up everything as a takeaway message, I guess the first main thing to note is that when we talk about Greybox parameter estimation, this is the natural framework, I would say, for estimating parameters of dynamic systems. Since we always have to deal with model approximations and model disturbances, measurement noise on inputs which we feed into the model for parameter estimation, this will inevitably give considerable uncertainty to the state estimation model that we are dealing with. And therefore it's very useful to understand this Greybox approach to parameter estimation so that we can make educated approximations and maybe still use the ballistic approach, but understanding the Greybox framework first allows us to be more sure what we do when we sort of deviate from this most general statistical foundation for parameter estimation. Another important point is this realization that this is sort of a layered cake approach, where we have the likelihood function as the basis. We can add priors to do the posterior distribution, and then we have different forms of algorithms which can compute with both likelihood and or posterior functions in order to obtain parameters. And whether we use numerical optimization or MCMC or some other approach to exploring parameter space, we still need this evaluation of likelihood and posterior functions. And then of course the likelihood function is depending on using the Kalman filter and so on to estimate innovation and innovation covariance and evaluate the log likelihood function in that way. But it really is sort of a very strong, complete framework for parameter estimation, where you have a lot of different options at different stages throughout the process. So it allows you to sort of pick and choose a bit how to set up your parameter estimation problem depending on what you are after. And the final important point is that because of this strong mathematical foundation, we have a lot of tools available to do things like model validation, model selection, and studying parameter identifiability, which many of the more simplistic parameter estimation techniques doesn't offer, because it's missing this solid statistical foundation that this Greybox framework represents. And therefore we cannot use the statistics on those methods. But here it's a definite advantage that we really can do a proper job of analyzing our estimated parameters in terms of ascribing a uncertainty or a confidence level, or indeed a probabilistic representation through an actual and empirical posterior distribution. So it is in sum a very powerful approach to parameter estimation, which I think is really worth to dig into. Unfortunately, it is theoretically complex. It consists of many different steps and many different algorithms, all of which you sort of have to understand a bit in order to use this effectively.